Now, you've probably been expecting this for a while. We've been learning how to take derivatives. So it's time for us to talk about what it would mean to undo the taking of a derivative. You're used to this process. You learned how to add, then you learned to subtract. Addition and subtraction are inverse operations. You learned how to multiply, then you learned how to divide. You learned how to square, and then learned how to take square roots. You learned about exponentiation, and then you learned about logarithms. So we learn about functions and their inverses sort of together as pairs. So an antiderivative is the result of undoing the derivative of a function. So let's think about what that would mean, because we have this problem that we haven't had with other functions when we try to learn their inverses. If I wanted to take the derivative of, here we go, y equals x squared, that's easy. Y prime is 2x. What if I want to take the derivative of y equals x squared plus 7? Well, here we go. The derivative y prime is 2x. So we can't tell the difference. We can't tell whether when we took the derivative, well, we can't tell when we get a derivative of 2x, whether we started with x squared, or x squared plus 7, or x squared plus 9.3, or x squared minus 103 million. So we're going to have to take that into consideration when we try to build the original function back from its derivative. So let's fill in part of your paper here. A function capital F of x is an antiderivative of little f of x if capital F prime of x equals little f of x. I'll write that in. So a function capital F of x is an antiderivative of little f if capital F prime is equal to little f of x for every single x that's in the domain of little f. So just for an example, we're going to try to figure out, can you name any antiderivative of sine of x? So you have to think back. So the better you know your derivatives, the easier this is going to be. Is there any function I could take the derivative of to get sine as the answer? So I could try some things out. Oops. Is y going to be, or is f, capital F, going to be, there we go, cosine of x? We could try it out. If I take the derivative of cosine of x, that's a parenthesis, is the answer going to be sine x? Now the derivative of cosine x is the opposite of sine x, but that can give me a hint. So I'm going to let capital F of x, which is the antiderivative of little f, be the opposite of sine of x. And now notice I asked for any antiderivative. That means if I take the derivative of negatives, if I take the derivative of negative sine x, I will get cosine x. This is a great answer. But watch this. Remember when I said I took the derivative of x squared to get 2x, but then I took the derivative of x squared plus 7, I got the same derivative, 2x. Any two functions that have the same slope everywhere, like these two functions, g and f, have the same slope everywhere. They're not the same function, but they would have the same derivative. So what's the difference between these two functions? You can see here in this picture, there is some constant difference between their y values. So if I picked an x value there, f of x would be something, g of x will be exactly capital C more than f of x at this place. So we're going to use this C, this idea that there could be some constant difference between all the functions who have the same derivative, to find specific antiderivatives, like the one on your worksheet. So here we go. Now I want to find a specific antiderivative of sine of x. It's the derivative of sine of x for which, if I plug pi in, I get 7 out. So here's our idea. Now anytime that we take an antiderivative, oops, we're going to remember that there could have been some number added onto the end of the original function that gets, you know, derivative into 0 at the end there. So try this. I'm going to let capital F of x equal, it has something to do with negative cosine of x, according to that problem we just did. But there could be some number added or subtracted here on the end. We're going to call that capital C, just for constant. That's a convention that you'll find used throughout calculus. So now I'm looking for some function. It kind of looks like this. It looks like negative cosine of x plus something. This is most of my answer, but I haven't finished. I haven't given a final answer until I can figure out what that something is. So I'm going to try plugging in this ordered pair that they've given me, and I'm going to see if I can figure out what C is. So I know capital F of pi should equal the opposite of cosine of pi plus some constant. So capital F of pi is supposed to be 7, and that's supposed to equal the opposite of the cosine of pi, which is the opposite of cosine of pi is negative 1, plus some constant. So 7 is equal to 1 plus c. I can decide that c has to equal 6. Now I can give my final answer. My final answer, capital F of x, the antiderivative, is the opposite of cosine of x plus 6. Final answer. All right, we got one more problem here. I know f of x is going to be 5x minus x squared. I'm supposed to find any relative extrema and name any intervals on which f is increasing and any intervals on which f is decreasing. So, I'm going to start by finding f prime of x, which is going to be 5 minus 2x. Critical points are any place where f prime equals 0, so 0 is 5 minus 2x. And I'm going to start with my number line here. So 0 equals 5 minus 2x when x equals 5 halves. It's the only critical point, and notice I've been given no endpoints. So I'm interested to know for what values of x is f prime positive, for what values of x is f prime negative. So if I plugged in some number to the left of 5 halves, let's say I plug in 0 for x, f prime is going to be 5 minus 0, which is 5, which is positive. And if I plug in a number bigger than 5 halves, I'm going to have a negative derivative. So now I've got an answer to parts B and C, which come up a little bit faster, and then we'll come back to part A here. So I'll type it up. So I've written up my answers to parts B and C. F is increasing anywhere f prime is positive, so f is increasing when x is less than 2.5, because f prime of x is positive there. And f is decreasing where x is greater than 5 halves, because f prime of x is negative there. So then the question that remains in our answer to part A is, what's happening when x is exactly 5 halves? So what we want to do is start to imagine this. I have a function, here's x equals 5 halves. This function increases before x is 5 halves. And then after x is 5 halves, it starts coming downhill. So decreases afterward. What's happening here? What feature of the function, what relative extreme value happens right here when a function which has been going uphill now starts to come downhill? Well, it's the location of a relative maximum. So my answer for A, f has a relative maximum at x equals 5 halves. So, and one other thing to think about, just to sort of confirm our thinking here. Imagine what this would look like if we graphed it. This quadratic function, the leading coefficient, the coefficient of the x squared term is -1. So this is a parabola that opens upside down. What kind of extreme values does it have? Well, it's going to have a maximum, both a relative maximum and an absolute maximum at that vertex. So that's exactly what's happening here. This x equals 5/2 is the location of the vertex.